What's up, everybody, and welcome back to OpenStax Algebra and Trigonometry, Chapter 10, Section 4, Polar Coordinates Graphs. Let's do it. Describe the three types of symmetry in polar graphs and compare them to the symmetry of the Cartesian plane. So I'm going to look at a graph on Desmos, and then I'll explain the type of symmetry you can find. So kind of like a regular graph, right? You could have symmetry across the x-axis, okay? You could also have symmetry across the line x equals pi halves, which is basically like symmetry across the y-axis, right? And then last but not least, you could have symmetry about the origin, okay? That could be like a circle or something like that. And of course, with polar coordinates, the origin is called the pole, but same idea. So those are the similarities, those are the types of symmetry done. What are the steps to follow when graphing polar equations? So first, we're going to test for symmetry. Then you're going to try to find the zeros. Then you want to find any maximas. And then you want to make a table. Now, of course, there are different types of equations, polar equations in particular. And once you kind of recognize the type, you might have a better idea of what the function is going to look like. So it's important to bear that in mind as well. And by the way, good theta values to use when you're making your table would be 0, pi halves, pi, and 3 pi halves, right? These are basic values on the unit circle as well. So that's how you do it. Done. What part of the equation determines the shape of the graph of a polar equation? So what it depends on is whether or not sine or cosine as a trig function is being used. And then it also depends on the constant that's in front, right? Whether it's 4 or -3 or something like that. So those are the different components that can affect the shape of a polar graph. For this question, we're going to check the symmetry based on the different symmetry tests, right? So this is how you test for symmetry on the polar axis, the symmetry to the y-axis, or in polar coordinates, theta equals pi halves, and to the pole, or in regular, that'd be the origin. Okay, so we're going to test this out. Now, first, we're going to test for polar axis symmetry. So when I plug in negative theta, right, what this is asking is, when I plug in negative theta, do I just get regular theta? I actually would, because when I take cosine of negative theta, if you remember the symmetry rules, cosine of negative theta is the same as cosine of theta, which means nothing changes in the function, okay? So when we plug in a negative theta, we get the exact same function, which means it does have symmetry to the polar axis. Now, when I plug in both negative r and negative theta, the r would flip, but the theta wouldn't. So it's not symmetrical to theta equals pi halves. And then for the pole, if I plug in negative r, it doesn't go back to the same equation, doesn't go back to regular r, right? That r would be negated. So it doesn't have symmetry to the pole either. So just the polar axis, done. So for this one, we're going to run through the different tests to test for symmetry. Now, I can see right off the bat that this is going to be a theta equals pi halves situation, because if I plug in negative r and if I plug in negative theta, right, to theta, so the theta is negative, sine has the property such that I can just pull the negative outside because it's odd. And then I have negative r equals -3 sine 2 theta. Negatives are going to cancel out. It goes back to normal. So I know I have symmetry here. Now, the other two tests are not going to pass. But remember, that's not indicative necessarily that it's not symmetric about the polar axis or the pole. So we know definitively it has symmetry about pi over 1/2 equals theta. But we end up also having polar axis symmetry as well as pole symmetry. Okay, we have all three. Now, even though it doesn't necessarily pass the other two tests, we still have that symmetry. So the test tells us for sure if you absolutely have symmetry, but if you fail, you still could. Now I'm going to show you the graph. So you can see with 3 sine 2 theta, it's symmetric in every single way, about theta equals pi halves, about the polar axis, and about the pole. So that's how you do it. Done. For this one, right off the bat, we can tell that the symmetry it's going to have is this one, because if I plug in negative r and I plug in negative theta, I got negative r equals -2 theta, divided by -1, they cancel out, and it goes back to the original. So I know I have this symmetry. Now, it's going to fail the other two tests, right? If I plug in negative theta, it's going to be different. If I plug in just negative r, it's going to be different. So this is the symmetry, and it actually doesn't have any other symmetry. So it's just symmetry with respect to theta equals pi halves, done. So for this one, when you run it through the typical symmetry test, you'll see that for theta equals pi halves symmetry, it actually passes, right? You plug in negative r and you plug in negative theta, the negatives are going to cancel out and you end up with the original equation. But the answer in the back of the book is actually no symmetry. And I want to show you why here that there's no symmetry. So if we go to the graph, you see that we clearly have something that doesn't have symmetry with respect to anything. Not with respect to the pole, not with respect to pi halves. So there definitely is no symmetry in the graph. Now I want to give one caveat. When you expand the range of theta, right, from negative 12 pi to 12 pi, now all of a sudden it does have symmetry. So I just want to point that out. But my assumption is that the back of the book is looking at this typical from 0 to 12 pi or whatever it may be, where there is no symmetry. So just a caveat, double check with your teacher what answer your teacher would like you to use or what type of logic they'd like you to use, but that's how you do it. Boom, done. So for this one, because we're taking a radical, if you remember that a radical is going to provide a positive and a negative answer, right? So when we bear that in mind when we run it through these tests, now the first thing is, right, we plug in a negative theta. That's clearly going to modify this, right? It's going to change the theta. It's not sine of negative theta is actually negative sine of theta. So I would negate the inside, and that would fundamentally change this, right? If I plug in both a negative r and a negative theta, we're going to have something similar, right? The r is going to be negated, but once again, this part's going to be changed. But with respect to the pole, it's kind of interesting because if I do plug in a negative r, it doesn't really change because if you remember, the square root's going to provide a positive and a negative response. We're already getting a positive and a negative. So when I negate the r, I'm not effectively changing anything. Now I want to show you the graph in Desmos. So again, this is confirmed. We do have symmetry with respect to the pole. So it's symmetric with respect to the pole. That's how you do it. Boom, done. Okay, so for this one, I'm going to plot it by hand, and I'm going to plug in a couple values for theta here and get the corresponding value for r, or an approximation thereof. So first, if I have 0 sine of 0 is 0 times 4 is 0. Pi 6, sine of pi 6 is actually 1/2 times 4 is 2. Sine of pi thirds is rad 3 over 2 times 4, okay, which would be 2 rad 3. Pi halves is 1 times 4 is 4. 2 pi thirds is again rad 3 over 2 times 4 is 2 rad 3. 3 pi fourths is rad 2 over 2 times 4, which is 2 rad 2. And then 5 pi 6 is again going to be 1/2. 1/2 times 4 is 2. So let's plot these points out. So again, we have 0 radians over here going out at r value of 0. We have pi 6, which is along this line, and that's a value of 2, so we can come out here. Then we have pi thirds, which is along this, and we have 2 rad 3, which is about 3.5. And then we have pi halves, which is going straight up, which is 4. And then we have 2 pi thirds, which is, again, 2 square root 3. And then we have 3 pi fourths, which is 2 rad 2, which is about 2.8, so maybe somewhere like here. And then we have 5 pi 6, which is 2. 5 pi 6 is 2. And I didn't put it here, but if we have pi, it's again 0, so we come back here. So what you can kind of see is we have a circle. And there we go, I kind of connected the dots. Now, if you continue to go around, you would just keep re-outlining the circle over and over. But that's what this is. This is a circle. That's how you do it. Done. So for this one, we're going to plug in these different values here. This will fit nicely and give us enough information to make a graph. So let's plug and chug. So first, we're going to plug in 0. Cosine of 0, if you remember from the unit circle, is 1. So it's going to be 2 times 1, and then 2 minus 2 times 1, which is 0. Cosine of pi fourths is rad 2 over 2 times 2 would just be rad 2. And then 2 minus rad 2. Cosine of pi halves is 0. 2 minus 0 is 2. Cosine of 3 pi fourths, that's negative rad 2 over 2. So then you multiply by 2 and you get rad 2. And then the negatives will cancel out, so you get 2 plus rad 2 over here. And then we got cosine of pi, which is negative 1. So 2 minus 2 times negative 1, that's 2 like this. And then 2 times negative 1 is negative 2. 2 minus negative 2 is 2 plus 2, which is 4. And then we have 5 pi fourths. That's again negative rad 2 over 2. So that gives us the same thing as 3 pi fourths, which is 2 plus rad 2. Then we got 3 pi halves down here. That's 0. 2 minus 0 is 2. And then we got 7 pi fourths. That's again going to be positive rad 2 over 2, which is going to be the same as this. So we got 2 minus rad 2. Now let's plot the points. So first we have 0 radians and a radius of 0. Then at pi fourths, we got 2 minus rad 2, which is about 0.6. So we'd say pi fourths, which is coming out here, and then 0.6, that's pretty small, right? Here's 1, so we're kind of like down here. Then we got a pi halves going straight up. We got 2, so up there. Then we got 3 pi fourths. We got 2 plus rad 2, which is about 3.41. So 3 pi fourths coming out here and right there. And then we have pi, which is 4, so coming out on the fourth circle. And then we have 5 pi fourths, which is the same as up here, 2 plus rad 2, which is about, again, 3.4. 3 pi halves coming straight down, that's at 2. And then again, 7 pi fourths is the same that we had at pi fourths, which is coming back to like around here. And now I'm going to do my best to connect the dots. It's going to look a little funny, but we're going to try. So let's say like this, coming back around like that. And the name of this is a cardioid, like that. Boom, done. So for this one, I'm going to choose values for theta that are easy to plug in and calculate mentally. And this is still going to go all the way around, so it's going to give us a nice full picture. So first, when we plug in 0, sine of 0 is 0, so 3 plus 0 is 3. Sine of pi 6 is 1/2, so it's 3 times 1/2, which is 1.5, plus 3, which is 4.5. Sine of pi halves is 1, so it's going to be 3 plus 3 times 1, which is 6. Sine of 5 pi 6 is again going to be 1/2, so that's going to be 4.5 again. Sine of pi is 0, so that's 3 plus 3 times 0, which is 3. 7 pi 6, that's going to be negative 1/2. So 3 times negative 1/2 is negative 1.5, plus 3 is 1.5. Sine of 3 pi halves down here, that's going to be negative 1. So 3 plus 3 times negative 1, that's actually going to be 0. And then sine of 11 pi 6, again, that's negative 1/2, excuse me. So then that's 3 plus 3 times negative 1/2. That's 3 plus negative 1.5, which is positive 1.5. Okay, now let's plot these out. At 0, here we've got 3. At pi 6, we have 4.5. At pi halves going straight up, we have 6. At 5 pi 6, we have 4.5, and that is coming out here. At pi coming straight across, we have 3. At 7 pi 6, we have right down here 1.5, like that. At 3 pi halves, we have 0 here. And then at 11 pi 6, again, we have 1.5. That's like right here. Okay, now let's connect the dots. And for this one, we have what is called a cardioid. That's how you do it. Done. So for this one, I got the following values. And the reason why I'm choosing pi 6, 5 pi 6 in particular, not every value on the unit circle, is because these are easy to calculate for sine because I can evaluate them mentally. So let me show you. So first I plug in 0, sine of 0 is 0, times 4 is 0, plus 7 is 7. And we're going to have the same result for 2 pi, so we know we have a 7 down there as well. Now for pi 6, sine of pi 6 is 1/2. 4 times 1/2 is 2, plus 7 is 9. So we have the same value here, and then as well for 5 pi 6. Now for pi halves, sine of pi halves is 1. So 1 times 4 plus 7 is 11. On sine of 7 pi 6. Now 7 pi 6 is going to give us negative 1/2. So we got negative 1/2 times 4 is negative 2, plus 7 is 5. That's going to be the same for 11 pi 6 because 11 pi 6 is also going to give us a negative 1/2. And we skipped over pi. Sine of pi is 0. 7 plus 0 is 7. And then 3 pi halves. Sine of 3 pi halves is negative 1. 4 times negative 1 is negative 4, plus 7 is 3. All right, let's plot these values. We got 0 coming out to 7. We got pi 6 on this line coming out to 9. We have pi halves coming straight up to 11. And then again, we have 5 pi 6 here, again, coming back to 9. We got pi coming out to 7. Notice the symmetry. We've got 7 pi 6 with a length, radius of 5. We got 3 pi halves going straight down, a length of 3. 11 pi 6 again, we got 5, and that'll do it. Now let's connect the dots. Okay, so this is a little wobbly. This is the best I could do. But notice you have like a little dip in here, and that's hard to see with the dots that we provided. If you wanted to see more specifically, maybe you could map out 4 pi thirds and 5 pi thirds, and you get a better idea. But it does kind of have this little indent that it goes in like that. And this is considered a one loop limacon, okay? That little curly thing on the C makes it limacon. So there you go. That's how you do it. Done. So for this one, because now we have cosine, I'm choosing pi thirds, 2 pi thirds, 4 pi thirds, and 5 pi thirds. Again, just because it's easier to calculate mentally. You can still do pi 6, you could do other values in the unit circle, but I'm going to use these and we're going to get a nice picture as a result. Cosine of 0 is 1 times 4 plus 5 is 9. Cosine of pi thirds is 1/2, okay? 4 times 1/2 is 2 plus 5 is 7, and that's going to be the same value from when we have 5 pi thirds. That's also going to return a positive 1/2, so we have a 7 here. By the way, 2 pi is also going to give us a value of 1, so that's going to come back to 9 as well, just like 0. Cosine of pi halves is 0, so 5 plus 0 is 5. Just like 3 pi halves is 0, so that's also going to be 5. Cosine of pi is -1. So 4 times -1 is -4 plus 5 is 1. And then we got 2 pi thirds, okay? So 2 pi thirds is in the second quadrant. Cosine is negative there, so that's -1/2 times 4 is -2 plus 5 is 3. Same with 4 pi thirds. Now as we plot these out, we got 0 at 9. We got pi thirds at 7. We got pi halves at 5. We got 2 pi thirds at 3. We've got pi over here at 1. And then we got 4 pi thirds again back out at 3. 3 pi halves down to 5. 5 pi thirds up all the way to 7. And that's about it. 2 pi, we come back to 9. And now let's connect the dots. All right, not too bad of a drawing. And this is again a one loop limacon, okay, with that little curly C thingy. And there you go. That's how you do it. Done. Okay, so here are the values that I'm plugging in for theta. Again, because it's sine, I'm choosing pi 6, 5 pi 6, etc. because they're easy to evaluate. They all evaluate either to 1/2 or -1/2. So let's go. Sine of 0 is 0. 1 plus 0 is 1. And sine of pi 6 is 1/2. 3 times 1/2 is 1.5 plus 1 is 2.5. We're also going to get the same value for 5 pi 6 because that also returns 1/2. Then for pi halves, that's 1. 3 times 1 is 3 plus 1 is 4. And then we have sine of pi is 0. So 1 plus 0 is 1. 7 pi 6 is going to give us -1/2. So 3 times -1/2, -1.5 plus 1, that's -0.5. 3 pi halves is going to give us -1. So 1 plus 3 times -1, that's 1 plus -3, which is -2. And then 11 pi 6, that again is that -1/2. 3 times -1/2 is -1.5 plus 1 is -0.5. All right, let's plot these. So we got 0 and that's 1. We've got pi 6 and that's 2.5, which is kind of right here. We got pi halves, which is 4. Then we got 5 pi 6 out here, which is going to be, again, 2.5 right there. And then we got pi, which is 1. Then we got 7 pi 6 coming out here, but that's negative. So that's actually going to shoot us back in the other direction right there to 1/2. Then we got 3 pi halves going straight down, but it's -2, so that pops us up to +2. And then we have 11 pi 6, which is going this way, but is negative. So it's again -1/2 going backwards right here. So this is a little bit weird, right, with the dots we plotted. But what it's going to look like is something like this as we connect the dots. So you can kind of see it coming across. And what we have is a loop within a loop. This is called an inner loop limacon. And remember, if you ever feel like you don't have enough points, just plot more values, plot more theta values and corresponding R values, you get a fuller picture. Anyways, that's how you do it. Done. All right, so for this one, these are the values that I've chosen to plug in. So let's go for it. Plug in 0. Sine of 0 is 0 times 7 is 0 plus 5 is 5. Sine of pi 6, that's 1/2. 1/2 times 7 is 3.5 plus 5 is 8.5. But also sine of 5 pi 6 is going to be 1/2, so we have the same value there. Sine of pi halves is 1. 1 times 7 plus 5 is 12. Sine of pi is 0, so this one's just going to be 5. Sine of 7 pi 6, that's -1/2. So that's 7 times -1/2 is -3.5 plus 5 is 1.5. We're going to get the same value for 11 pi 6, so that's 1.5. And then sine of 3 pi halves is actually -1. So that times 7 is -7 plus 5 is -2. All right, so let's plot these out. We got 0 coming out at 5. We got pi 6 coming out at 8.5. We got pi halves coming up to 12, so that's a big one. And then we got 5 pi 6 again at 8.5. Pi coming out to 5. And then 7 pi 6 coming out to 1.5 right out here. We got 3 pi halves coming down at -2, which means we go backwards up here to 2. And then once again, 11 pi 6 is that 1.5. So as we kind of draw it out, this is what it looks like. We kind of bring it across like this, and then this does a little loop thingy, like so, and then keeps going. So there's our graph, and this is an inner loop limacon, like so. That's how you do it. Done. So for this one, because it's cosine, I've chosen these particular values primarily because they're easy to calculate mentally. Of course, I could do pi 6, I could do 5 pi 6, etc., other values in the unit circle, pi fourths, but I've chosen these because this will give us a clear picture and they're easy to calculate mentally. So let's start with 0. Cosine of 0 is 1. 5 plus 6 times 1 is 11. Cosine of pi thirds is positive 1/2. So 6 times 1/2 is 3 plus 5 is 8. We're also going to get positive 1/2 for 5 pi thirds in the fourth quadrant, which will give us that same output of 8. Then we've got pi halves. Cosine of pi halves is 0, so 5 plus 0 is 5. That's going to give us the same result for 3 pi halves. For 2 pi thirds and 4 pi thirds, that's going to give us negative 1/2. So 6 times negative 1/2 is negative 3 plus 5 is 2. We got the same with 4 pi thirds. And then, of course, cosine of pi is negative 1. 5 plus 6 times negative 1 is 5 minus 6, which is negative 1. Now let's plot these. We've got 0 radians corresponding with 11. We've got pi thirds corresponding with 8. We've got pi halves corresponding with 5, right? Going up straight to pi halves. We've got 2 pi thirds right here corresponding with 2, just 2 circles, very small. And then we got pi going out this way. It's negative 1. That means it kind of goes the opposite direction. So now we're coming out here on that 1 circle. And then we come to 4 pi thirds again, we're at 2. So that's right here. Then we've got 3 pi halves, that's 5, so that's coming down here. And then we got 5 pi thirds, which is 8, which is coming here. So now let's connect these dots. So you can see we have this interesting one up here, so it kind of goes in, and then we bring it all the way around. And here we have another inner loop limacon. That's how you do it. Done. So for this one, I'm choosing actually all of these values just up to here, right? Everything that's pertinent in the unit circle. And this is actually going to be pretty nice because we're doubling each angle. So even with cosine, it's going to be easy to calculate. But again, if you need to use a calculator or need to look at the unit circle to give these approximate values, no problem. Anyways, let's take it away. So we plug in 0 for theta. Cosine of 2 times 0, that's cosine of 0, which is 1 times 10. And here's the thing, we've got r squared equaling 10, right? So if I have r squared equaling 10, I have 2 different r values, right? Because I have the square root of 10, but it's plus or minus. So I have plus or minus radical 10. Same with pi 6 and all these other values, we're gonna get 2 answers. So now we plug in pi 6. 2 times pi 6 is actually pi thirds. So what's cosine of pi thirds? That's 1/2. 1/2 times 10 is 5. So here we've got plus or minus square root of 5. For pi fourths, we're doubling it to pi halves. Cosine of pi halves is 0 times 10 is 0. So here we got a nice 0 value. For pi thirds, 2 times pi thirds, that's 2 pi thirds. Cosine of 2 pi thirds is actually negative 1/2. So let me get negative 5. R squared cannot equal negative 5, right? This is not going to give us a real number. So we don't have to worry about plotting that here. Then we got cosine of 2 times pi halves. 2 times pi halves is pi. Cosine of pi is negative 1 times 10 is negative 10. Again, r squared can't equal negative 10. That's not a thing, right? Just we'd get an imaginary number. So that's not going to be real. Cosine of 4 pi thirds is going to give us negative 1/2 again. So this is a negative value. That's not going to work. And then we double 3 pi fourths. That's going to be 3 pi halves. Cosine of 3 pi halves, that's actually 0. So it's going to be the same as the pi fourths. Boom. And then we got 5 pi 6. And if you double that, it's going to be 5 pi thirds. So this is going to be similar to pi thirds in the first quadrant. That's going to give us 1/2. 1/2 times 10 is 5. Square root of 5 is the answer, plus or minus rad 5. So now we have some good values. Let's plot them out. So when we've got 0, we've got 2 values, positive square root of 10 and negative square root of 10. And that's about 3.16. So For 0, we're going to go out to positive, let's say here approximately, and the negative, so also on the other side here. For pi 6, we've got square root of 5, which is 2.24 approximately, and positive and negative. So pi 6, we go let's just say 2.2 and negative 2.2. So you can kind of see what this is shaping up to be. Then we got pi fourths, and that's 0, right? Pi fourths will come out here, and we got a 0 value. And these are all nothing we can plot. 3 pi fourths is again going to land here. And then 5 pi 6, we have that plus or minus rad 5. And again, that's about 2.2. So 5 pi 6, we got 2.2. And then we also got a 2.2 over here. So we can fill in the values more if you want. You could even try other values later in the unit circle. But you're going to kind of get this repeating pattern. It's going to kind of overlay it. So this is enough to connect the dots. So let's do that now. And you see it kind of makes this interesting figure 8, almost like an infinity sign. This shape is called a lemniscate. That's how you do it. Done. So for this one, I've chosen the following values. I've chosen things that are not typically on the unit circle, like pi 12s, 5 pi 12s. But the reason why is because we're going to be doubling them in here. And that is still going to be easy to calculate based on our knowledge of the unit circle. So this will give us a nice clear picture. So we're going to start with 0. 2 times 0 is 0. Sine of 0 is 0. So this is going to give us an R value of 0. And the same thing is going to be true for pi halves, right? We double pi halves to pi. Sine of pi is 0, so we got 0 there as well. Now we take pi 12s, double that, it becomes pi 6. So sine of pi 6 is actually 1/2. So 1/2 times 10 is 5, and then so here we got plus or minus square root of 5. Remember, it's positive or negative because that r is squared. So we got both values. And this is going to be the same thing as when we got 5 pi 12s, because we double that, that's going to be 5 pi 6. That also returns a value of 1/2. So this is also plus or minus rad 5. Now we got pi 6, we double that, that's pi thirds. Okay, so sine of pi thirds is rad 3 over 2. Rad 3 over 2 times 10 is 5 rad 3. And then because it's equal to r squared, we have to take the square root of that. So it's kind of like a double square root, and that's a plus or minus. That's going to be the same result as when we plug in pi thirds, because when you double it, that's 2 pi thirds. So right, sine of 2 pi thirds and sine of pi thirds, those are going to give equal values. So this is also going to be plus or minus rad 5 rad 3. Last but not least, we got pi fourths. You double that, that's pi halves. Sine of pi halves is 1, and 1 times 10 is 10. So here r would be plus or minus square root of 10. All right, now we got enough to plot this. Let's do it. So we got 0 is 0. Then we got pi 12, which is along this line. That's going to be plus or minus rad 5. So rad 5 is about, let's say here, but also the negative. So we got to go back this way as well, like that. Rad 5, rad 3 is about 2.9. So we got pi 6, that's about, let's say it's close to 3, right? But it's also negative 3 as well. So we come back this way, negative 3 like this. And then we have pi fourths. So that's going up this way. And that's the big one. That's rad 10. And that's about 3.2. So let's say just out here. But again, it's plus or minus. So we also got to go back this way like this. You can kind of see what's happening here. And then we come to pi thirds. We got the same values in pi 6. So pi thirds might be out here. And also the negative would be out here. Then we got 5 pi 12ths, which is plus or minus rad 5. So that's again going to be up around here. But we also got to come back to here, the positive or negative. And then pi halves is 0. So you see we got a nice little shape here. So let's connect the dots. And this is also called a lemniscate. That's how you do it. Boom, done. Okay, so for this one, I picked out the following values to plot this out. So I'm going to plug and chug and see what happens. Again, this is just kind of a sampling just to give you a rough idea. So we plug in 0. 2 times 0 is 0. Cosine of 0 is 1 times 3 is 3. We got pi 6 times 2 is pi thirds. Cosine of pi thirds is 1/2. So 1/2 of 3 is 1.5. Then 2 times pi thirds is 2 pi thirds. Cosine of 2 pi thirds is negative 1/2, okay? Negative 1/2 times 3 is negative 1.5. And we got 5 pi 6 out here. Doubling that is 5 pi thirds. Cosine of 5 pi thirds is 1/2 times 3 is 1.5. Cosine of pi times 2, so that's cosine of 2 pi. That is, again, 1. 1 times 3 is 3. Then we got 7 pi 6. If we double 7 pi 6, that's 7 pi thirds. Now that's not on the unit circle because that's more than 2 pi. But we can, 7 pi thirds, we can get a nice reference angle by subtracting 2 pi, or 6 pi thirds, which is the same as pi thirds. So we already know cosine of pi thirds is 1/2. So once again, we're back to 1.5. So for 3 pi halves coming down here, if we double it, that's cosine of 3 pi, coterminal with pi, right? You subtract 2 pi. Cosine of pi is -1. So here we got -3. And then we got 11 pi 6. And if you double that, that's 11 pi thirds. Again, to get a coterminal, we subtract 2 pi, or 6 pi thirds, and that's 5 pi thirds. Cosine of 5 pi thirds is back to 1/2. 1/2 times 3 is 1.5. So let's see what we get here. We got 0 coming out to 3. We got pi 6 coming out to 1.5. We've got pi thirds this way going out to -1.5. So we got to go in reverse like here. And then we got 5 pi 6, which is 1.5. Boom. Then we got pi coming out to 3. We've got 7 pi 6, which is 1.5. And then we got 3 pi halves, which is -3. So 3 pi halves coming down, but it's -3, so we got to go back up. And then for 11 pi 6, we got 1.5. So 11 pi 6, and we've got 1.5. One thing actually I forgot, I just realized, is pi halves. So let me throw it on here. That's always one I like to include, and it's important for this one. So if you double pi halves, that's pi. Cosine of pi is -1 times 3 is -3. So pi halves is -3, which means we got to go backwards, and that's nice. And by the way, I want to do actually one more too. I also want to do pi fourths. I did skip that as well. I'm going to throw it in right here because when we double pi fourths, that's pi halves. Cosine of pi halves is 0. So that gives us a 0 point here. So now that we got these points, let's kind of connect the dots. And this is sort of what it's going to look like. We've kind of got this interesting shape. So now we're going to kind of connect the dots like so. And we've got this interesting shape. It almost looks like a clover or a flower, and it is named accordingly as a rose curve. So that's how you do it. Boom, done. So for this one, I'm choosing kind of weird values. You might be like, wait a minute, these are not on the unit circle. But the reason why is because I took some typical values that I would use for sine, right? Like pi 6, because it's easy to calculate. Pi halves, 5 pi 6, and I've just divided them by 4 because I'm going to multiply them by 4 again, so you'll kind of see what this looks like. So first we start with 0, of course. 4 times 0 is 0, sine of 0 is 0, so that gives us a nice easy 0. And then with pi 24 times 4 is pi 6. Sine of pi 6 is 1/2, times 4 is 2. 4 times pi 8 is actually pi halves. Sine of pi halves is 1, times 4 is 4. Next, we got 5 pi 24ths. Again, when you multiply by 4, it's 5 pi 6. That gives us, again, 1/2. 1/2 times 4 is 2. Then we got pi fourths. 4 times pi fourths is pi. Sine of pi is 0, so this gives us a nice 0. 7 pi 24ths times 4, that's 7 pi 6. Sine of 7 pi 6 is -1/2 times 4 is -2. We got 3 pi 8ths, which times 4 is 3 pi halves. Sine of 3 pi halves is -1, so we got a -4 here. And then we got 11 pi 24ths times 4, which is 11 pi 6. Sine of that is -1/2 times 4 is -2. This gives us a nice little smattering of potential values. I'm going to give you more in a second to really fill out the graph, but let's plot these to start. So we got 0, 0. We got pi 24ths, which is 2. Pi 24ths will be halfway between pi 12ths and 0. So we're coming out here at 2. Then we got pi 8ths. So this is pi fourths. Halfway between that is here, and that's going to give us a nice value of 4. And then we got 5 pi 24ths, which is, again, our value of 2. We got the pi fourths at 0. We already got a 0 here. And then we got 7 pi 24ths. That's right in here, but that's -2. So that'd be like right here. 3 pi 8 somewhere in here, let's say, and then it's going -4. So we're coming down here. And then we got 11 pi fourths coming up somewhere here, but it's -2. So we'd say come down back like this. All right. So this just gives us like a little sampling. And you see it kind of makes this interesting shape here and coming around here. Now, as you plug in more values, what you'll find is the rose pattern continues, right? This is just a smattering of potential inputs and outputs. But as you kind of keep going around the unit circle with the appropriate values, this is what it's going to eventually look like. a rose curve with petals that all extend out by a length of 4 on all of these, right? Boom, boom. And it's not the best drawing, but that gives you the idea. This is a rose curve. That's how you do it. Done. So this one is a typical Archimedes spiral, okay? And you can just kind of tell from the format r equals theta like that, but it's negative theta. And I'm not going to do a table value, but in general, you see that the radius or the r value is equal to the negative theta. So if you think about it, when theta is 0, r is 0, right? So we're right here. And then as theta expands, r kind of expands, just going negative. So just to give you an idea, right, at pi fourths, the r value is going to be negative pi fourths, which is pretty close to negative 3/4. So we kind of get like an idea of this. And then let's say we have pi halves, which is like 1.5 is going to be negative 1.5 coming down here. Then we've got pi, which is, let's say, about 3, but then that's going to be negative 3 going this direction. So you can kind of see the order that it's going like this. And, I could plot more points. This is just an approximation, but it's a spiral. That's roughly how you do it. Done. This one here is going to be an Archimedes spiral, and we can tell just by the basic format, right? R equals theta, but here it's got a multiplier, and it's a negative 3 theta. So if we want to think about a couple of points just as an example, right? If I've got 0 for theta, of course, R is going to be 0. But then let's say I've got pi thirds, okay? Well, negative 3 times pi thirds is just going to be negative pi, which is about negative 3. So pi thirds, we got negative 3 coming down about here. Maybe I can even back up and do pi 6. Negative 3 times pi 6 is negative pi halves. So that would come back this way to like negative 1.5. And let's do pi as well. When it's pi, negative 3 pi, so pi, but negative 3 pi, that's going this direction. It's pretty close to like 9 something, maybe 9.5. So you can kind of see the general idea. So what this is doing is it's spiraling out in this direction. Oops, not the best example, but something like this. And then it continues out. So that's it, Archimedes spiral, done. So for this question, we're asked to graph this in a graphing calculator. So we're going to use Desmos, and I'm going to show you how now. So in Desmos, you just want to make sure that you've chosen this option, right? This is the typical grid. So we're in this option here, and then we're going to plug it in. And here's the graph. If you zoom in a little bit, it looks more like kind of what's presented in the book, but this is a more complete picture. And that's how you do it. Boom, done. For this one, they asked us to use a graphing calculator, so we're going to plug it into Desmos now. Just make sure that you've selected this mode in the grid so you can see this correct format. And here we go. We get this cool little looking hippopede thing, and that's how you do it. Done. For this one, it says to use a graphing calculator, so we're going to do that in Desmos now. Just make sure you're in the right mode here, which is this mode. This gives us this nice graphing mode for polar equations. And here we have the graph. It almost looks like a peanut, which is kind of cool. But anyways, that's how you do it. Done. For this one, they want us to use a graphing calculator, so we're going to use Desmos. And once again, just remember to make sure you're in this correct mode here. And from what we've seen in previous examples, we kind of knew this was going to be an Archimedes spiral like this, but if you zoom out, you can kind of see that's what it looks like. That's how you do it. Done. For this one, they want us to plot the graph in Desmos, so we're going to do that now. Just make sure you've not selected the grid, but this mode. And here we get this really cool shape like this. If you zoom out a little bit more, you get a clearer picture. That's how you do it. Done. So for this one, they want us to graph both of these in Desmos in a graphing calculator and then compare the graphs. So let's do that now. So you notice I did adjust the domain of theta, right? Because they did say from 0 to 4 pi. So that's just one thing I did. But let's look at them one at a time. You see the green one, the top one, r equals theta. That's a nice Archimedes spiral. And the purple is also a nice Archimedes spiral. So they're quite similar. What you can see is that it almost looks like the purple one is shifted up a little bit. So they're very similar, but there's just like a slight transformation, but definitely both Archimedes spirals. That's how you do it. Done. So for this one, they want us to use a graphing calculator to graph both of them and then compare. So let's do that now in Desmos. So here's the first one, r equals 2 sine theta over 2 from 0 to 4 pi. And you see it's this like really cool looking shape. And then let's look at the purple shape. And it's very similar, right? If I take away the green, you can see it's very similar. It's been sort of like rotated slightly and then kind of like disfigured a bit, but it's very similar. And one thing to note is you can kind of see that they both contain these two loops, right? But that's the gist of it. That's how you can kind of compare and analyze them. Done. So for this one, they want us to graph it on a graphing utility with these different parameters for theta. So let's do that now and we'll compare the differences. So here's the first graph, right? And this is just from 0 to 4 pi. And it looks like we got 1, 2, 3, 4, 5, 10, 15 different petals, but it's a really cool looking figure. Now we're going to increase it to 8 pi. So let's turn this, let's add this and kind of turn this off. So it looks the same. Actually, we can leave that on because it kind of overlaps it, right? But now it's more petals, right? So we see that this is the increasing the domain of the thetas increases the number of petals. Now we're going to do it again to 12 pi. Boom, even more petals. And then last but not least, 16 pi. So that's how you do it. Done. So for this one, we're going to graph the three equations in a graphing calculator, aka Desmos, and then we're going to compare the similarities and the differences. So you notice the difference between these three equations is the coefficient, right? So when I have a 3 in front, just notice we got 3 petals and notice the size. Now with the 2 in front and this one in black, look at that, it's shrank. So the coefficient seems to relate to the length of sort of like the longest part of the petal, right? You notice there's a 3 there, it goes out to 3. Now there's a 2 here, it goes out to 2. So with this one with no coefficient, I assume it's going to go out to 1. Let's see, and boom, that is confirmed. So it kind of shrinks that length of the petal at the longest point of the petal. So that's how you can compare. So for these three, we're going to graph them on a graphing utility, aka Desmos, and then we'll compare. And if you remember, these should provide Archimedes spirals, so we'll see how the different coefficients affect the spirals. So I'm going to kind of start with r equals theta. As we expected, it's a classic Archimedes spiral. Now we got 2 theta, and look what happens. It looks like it's kind of been expanded, right? It's larger, it's bigger, so it's expanding out at a greater pace. So we can assume that for the 3 theta, the same will be true. It's going to be even bigger, and you can see that in green, that is actually true, right? You can see at a smaller level here, it's extended out farther as it goes, so it's like a bigger spiral. So we can say the smaller the coefficient, the tighter the spiral, the larger the coefficient, the wider the spiral, if you want to say it like that. That's how you do it. Done. So for this one, we're going to graph both of these equations, then we're going to find the points of intersection, so let's do that now in Desmos. So as we've seen in previous problems, right, when r equals just a constant, we know it's going to be a circle. And let's look at these two, and we can find the intersection right here in Desmos, which is going to be at a theta value of pi thirds and an r value of 4. And here a theta value of 5 pi thirds, but also an r value of 4, right? The r is the radius, right? 1, 2, 3, 4. So we've got 4 comma pi thirds and also 4 comma 5 pi thirds. That's how you do it. Done. So for this one, we're meant to graph these and then find the point of intersection. So let's do that in Desmos now. So here are the two graphs. And if you kind of zoom in here, it looks like the points of intersection are right here and right here. And this one looks like it's at pi thirds right at 1.5. And this one is also at 1.5 for the r value, but then it's at 5 pi thirds. So we can say 1.5 or 3 halves at pi thirds and 3 halves at 5 pi thirds, and that's how you do it. Done. For this one, we're going to graph both of these in a graphing calculator, aka Desmos, and find the points of intersection. So let's do that now. So for this one, when we look, the only point of intersection I'm really seeing here is right here at the pole. That's where they both cross. And as you kind of trace the path around, it looks like it's hitting that pole right when the theta value is, so the radius is always going to be, the r value is always going to be 0, but it looks like it's hitting it at 0 if we kind of trace the trajectory, and then coming back also at pi halves, right, going straight up, and then it kind of loops around, comes back again, intersecting in at pi, and then again at 3 pi halves. And if we're including 2 pi coming all the way back around, again, we would say 2 pi. So those are 4 intersection points, so let's write those out. So again, as I mentioned, in every case, the r value is 0, and then it's sort of those 4 main points on the unit circle, right? We're starting at pi halves, pi, 3 pi halves, and then 2 pi. Or of course, you know, I said 0, you could say 0 instead of 2 pi or whatnot. But this is how they had it in the back of the book, so that's how I'll do it. That's how you do it. Done. For this one, we want to compare the graphs and find the points of intersection, so let's do that in Desmos now. So for some reason in Desmos, it doesn't like when I say r squared. So what I did was I instead took the square root of both sides, but I included the plus or minus. So we have 2 functions representing r squared equals sine theta and 2 functions representing r squared equals cosine theta, but it produces the same result. So now we can see we got these 4 points of intersection, and the theta values for where the intersection points are occurring are at pi. Here, let me zoom out a little bit so you can see. It's like pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. Now to pinpoint that R value is a little bit difficult. We can see it's a little bit less than 1, but we can find that, I'll tell you the exact value just based on what's in the back of the book, and we can write it out that way. So this is the exact R value as presented in the back of the book. And again, remember, it's the same for all of these. It's the 4th root of 8 divided by 2, and the actual value of that is like about 0.84, so it's what we kind of estimated. And as I mentioned, we have it occurring at radian values, or theta values, excuse me, of pi fourths, 3 pi fourths, 5 pi fourths, and 7 pi fourths. That's how you do it. Done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more from the Scalar Learning channel, make sure to click subscribe. Thank you guys so much for joining, and I'll see you in the next video. Take it easy.